Yes, so this is a talk about some work that was actually primarily done by my an undergraduate student doing a project with me, Henry Calver. But so he knows all the real details. I'm presenting the work. So what this is about is it's about yes, the very most basic form of adaptive optics. So the picture on the left here is from 1984. So this is the Laird-Thompson's system. It's a tip-tilt system, so that is lowest order AO you can build. But it turns out, yes, that this kind of low order AO is still relevant today. So picture here is the Magdalena Ridge Observatory Interferometer. This is the first telescope of hopefully 10 telescopes. It's a 1.4 meter telescope, and it's an interferometric telescope. So it turns out that if we working in the K band, when tip tilt at 1.4 meters is actually perfectly good correction for the telescope. So tip tilt is back. So, but it also turns out, of course, that things like a Shack-Hartman sensor also measures tip tilt. So this is relevant to perhaps all kinds of adaptive optics. Okay, so what I'm talking about here is the effect of centroid anisoplanatism, which is hard to say, but relatively easy to explain, which is the idea that higher order wavefront errors will leak into your measurement of tip tilt. And so what this diagram is showing here is that if you have a wavefront which has some third order coma aberration here, and you compare what a center of mass measurement of the position of a star would give you, well, the classical result is it actually gives you the average wavefront tilt. So if you take the average wavefront tilt, then you get basically that the wavefront isn't tilted at all. But if you ask what the Zernike tilt is, which is actually the mean square best fit to the wavefront, it's this red thing here. And so you can see there's an error between these two tilts. And yes, obviously in an interferometer, at least we want to minimize the mean square residual. So we want the Z tilt, the Zernike tilt, but what we actually measure is the G tilt. And it's the difference between these two that is the problem that adds to our error budget. So if you actually ask yourself, okay, so how do different algorithms for doing a centroid actually respond to these this leakage of high order aberrations? It turns out that they respond in different ways depending on how you process the image. So this is the classical here. The centroid is the classical center of mass algorithm, but there are various other centroidic algorithms you can use. And it turns out actually that if you vary the coma coefficient, the error you get varies differently with different algorithms. So how you process the image clearly matters. And you can imagine, in fact, that's the first idea we had, was simply to average various different image measures, and you might cancel out the centroid anisoplanatism. Turns out that doesn't really work. A linear solution just doesn't work. So we can go to a nonlinear solution. And of course, nonlinear solutions are now all represented by neural networks. So basically, this is just saying, okay, what we did was to apply standard convolutional neural networks to try and measure the centroid in a way that actually gives you the Z tilt, not the G tilt. And here's just this image is just showing the simulated images that were used to train, or at least an example of some simulated images that are used to train the wavefront. Because we know what the tilt is, we can just feed that into the neural network and train it on that. And I just wanted to use this this moment to quickly plug the Megascreen program, which is used to generate these wavefronts. It gives you accurate wavefronts, including the tilt. But does it generates it 10 times faster than real time in Python on a single CPU. So it's pretty fast and pretty accurate. But basically, yes, you train up a neural network and ask it to generate the Z tilts from the data, from the images. And here's the result, is that if you have nice data, indeed, on the right, you can see what the residual error is from the normal center of mass measurement. This is the centroid anisoplanatism, the residual error between the G tilt and the Z tilt. But here, this is the residual error of the neural network, and you can see it's a large factor smaller. So the typical problem with neural networks is that they only work on the data they're trained on. But actually, it turns out that this is showing now here. This is a neural network that's trained on a D over R naught of 10. And indeed, it does work at a D over R naught of 10 very well. In fact, we get a factor of nearly 7 improvement in the residuals from the centroiding. But actually, over a relatively broad range of D over R naughts, we're getting factors of at least 5 improvement. And in fact, we never get a factor of less than 1 improvement over a very wide range of seeing. So I think this is showing it's a relatively robust algorithm. It works really well. Obviously, you'd actually want to train your neural networks on a range of seeing and apply the neural network approach approximating to the seeing that you're actually seeing in order to get the best results. So yes, the other things you have to think about, though, is the other real world considerations are, for instance, that your images may be undersampled. I didn't actually think that was going to be a problem, but it turns out, because I was assuming that, in fact, it's the large scale features of the image that allow you to tell about the higher order aberrations, but it turns out that's not true. So basically, this is a plot of the improvement of the neural network versus the center of mass as a function of undersampling. So one is Nyquist sampling. So for Nyquist sampled image, we do fine. The moment we go beyond Nyquist sampling, in fact, the aliasing seems to cause a problem. So we would degrade to about a factor of 2 improvement if we undersample the image. And so we're working on additional things like looking at the effects of noise and so forth. But I think what we've shown is that a neural network clearly can tell from an image what the Z tilt is, even though the center of mass can't. And I think that's it for my presentation.
Okay, thank you very much. Thank you for this interesting presentation. We have some questions maybe. A question by Tim Morris. How does the computational load of the neural network compare to that of the COM algorithm?
Yeah, so clearly it's a lot less efficient on CPU time. We weren't really worried about that for this proof of principle, but on a 32 by 32 image, you can easily run in less than a millisecond. It's not a problem. But yes, it needs further work to make it a true real-time algorithm.
Okay. So thank you very much, David.